On to reviewing Itermute. Um, is there anything that you want me to talk about more here? Because we talked about a lot here, and this is probably the trickiest code we've seen so far, certainly. I think the code that we'll be dealing with today will actually be simpler.
So, I guess it's a topic from really, really far away, but
Oh, sure.
the option itself. So,
Yeah, yeah.
in my mind, it was uh, more or less like a struct, where it just tells you, okay, so this is uh, like I'm this type of object, and that's what this object can return or give you. But apparently, it's on its own object itself, or how does the option itself?
Okay. So it is a data type. It's not a struct, it's an enum. Let me bring up the definition. There's going to be a lot here, but what matters are these two lines. So it's generic, so it's an option of something, of some type T. And then it's an enum. I'll just rewrite it here. It's a... Oops. So what this means is we have two cases. We have none and we have some. And in the some case, we have an instance of the type T. But in the none case, we don't have anything. And this is tricky. I mean, this is different from enums in most other languages where you just have like a list of options. In Rust, enums can have, what is it? Enums can have, I call them payloads. I don't know if that's the technical term. But they can have data inside a variant. So I could have like something like, well, if you're none, you get an I32, and if you're some, you have a T. And then if it was an option of I32, then it would just be both two different ways to have an I32, but you could tell between them, right? But if it was anything else, then some would be of that type T, you know, but none would always be of type I32. I don't know. You can do things like crazier too. You can have like multiple fields in the variant, or if you want, you can also use a more struct like syntax. So it's like now I have an enum. This is not option anymore, but now I have an enum where either it's none or it's some of a struct that has an X, which is of type T, and a Y, which is of type I32. So what I can do here is I can, like, this is really best to think about in the context of pattern matching, where I could then do something like match on, uh, let me take this and put it in its own file. So I can create an instance of this enum, and the syntax for that is a little funny. They're namespaced within the enum. So I say foo : none. Okay, so now foo, let me do that so that it's gonna show me better things. I just inserted the mod in the main so that it's like part of the project actually. If it wasn't, then it wouldn't be part of the project and my tooltips wouldn't work well, like these things. But right, so here we have foo, which is of type foo, but it doesn't know the generic parameter because I just said none. So that doesn't actually constrain what t is, right? If instead I'd said it's sum of x has, pick a type that we've seen that's not an integer.
a box.
A box, sure. A box of what?
Okay.
You could
Yeah.
say integer or whatever. I don't care.
Yeah, box of integers. Let's go.
Okay. Yeah. Um so now it knows what type it is. It says it's a foo of box I32, right?
Hmm.
But now what I can do with this, and this is pretty silly because like I know exactly what it is because I just declared it, but I can match on foo, and then I can actually tell it to fill match arms, which says, create a match statement that actually matches everything. So now I can do something if it's none, but I can do a different thing if it's some, and I have these variables to play with. So I can do like println uh, x, y, and then this should uh, let me run a let me do this god awful thing where you create a function in the test and then you make it panic so that it prints the output because it swallows the prints otherwise. So here all I do is I run bruh, but it's not going to like that, right? Oh, it's also that's wrong. And that's not right. It should be recursive call site. No, it's not. And now it doesn't like it because just, so this just imports everything from this module. So now when I'm going to panic it here so this fails. Um, and the reason why I'm making it fail is because otherwise the test system doesn't actually print any of the outputs of the tests. The idea is if you are printing stuff in tests, you probably only care about that if the test failed. If the test passed, it's fine, you know. But I'm like abusing it. Like this is not how you're supposed to do it, but this is just like a simple way of getting it to work. Cargo test, it's gonna fail, but it actually is failing for other reasons. Let's see. This is for, why didn't I try this? Okay, 1 second. Okay. Oh, okay, we're fine. I had like not saved or something. It's not important to understand those errors. I don't understand them. I had not saved this thing, so this was having problems. But here we have, we're printing 7 9, right? Which is what we expected because it prints X and then it prints Y, right? Are you following?
Yeah, yeah.
Yeah. So
So,
enums, so the way to think about enums is that they are types with different values, and sometimes those values in turn have other values inside them. So different like options, and then yeah. So option is a really good example of that. Um, because it's just there, it just sort of represents the notion that we might have this thing, uh, but we might not. It's effectively nullable, right? It's we use at the same time when we would use the fact that pointers can have a null value in C. Because in C, the way to represent I don't have one of these things in this field is to say, well, let's make the field a pointer, and then let's set it to null. Because if I have an int pointer of type of an int pointer with the value null, that means there could be an integer here, but there isn't, right?
mhm.
So in Rust, because references and boxes and all of the types that are just pointers, they don't have a null case. Instead, we use option, which in those situations, and only in those situations, which allows us to have like an end to the list. Because in C, the list would just have a pointer to, like, the node would just have a pointer to another node, and at the end of the list that would be null. But here we couldn't do that because then we'd always have to have another thing. We couldn't just have a box, so we need an option of a box. Does that make sense?
Yeah, yeah,
Yeah, yeah.
I see.
Um, Other things to understand about option, though. This is an enum of other things to understand about enums. Okay, so how do they actually get stored? Well, this data gets stored just like it would in a struct. You've just got some bytes for X and you've got some bytes for Y, right? But how does the enum overall get stored? Well, the enum needs to know a couple of things, needs to store a couple of things. It needs to store the largest payload. So if I had like another variant that just had an I64 in it, right? Then whichever one of these, this one or this one, is bigger, that determines the overall size of the enum, or at least that has to determine it. The enum has to be at least that big. So the enum has to be at least 64 bits big here. But if T was some huge thing, which right now it kind of is, a box is 64 bits all on its own because it's a pointer on a natively sized pointer, right? Or it's just a pointer. And on our system, that's a 64-bit thing because we have a 64-bit processor. So this already is 64 bits, and this is another 32. So I guess this is 96 bits. But there are other reasons we actually round up so that if we had this and then immediately after, like if we had an array of foos, then we would have like then we need to be able to line the foos up next to each other, right? And they need to each have a certain alignment. So there are rules for alignment in CPUs that make it faster to access things like 4-byte integers if they are at an address that is a multiple of 4. Or 8-byte integers are faster to access if they're at an address that is a multiple of 8. In fact, on certain architectures, it's impossible to access an 8-byte integer unless it's at a multiple of 8. It's just like if you think about how the assembly would look, the assembly will do something like load 8 bytes from memory, right? Before it does anything with the 8-byte thing. And that instruction, that load 8 bytes from memory, is for some reason in the circuitry either optimized to work fastest if the address is a multiple of 8, or it only works for addresses that are multiples of 8.
I would assume it's
Yeah.
because of it's really easy to implement with an adder.
Maybe it's
So
an adder, maybe it's something else. I don't know. But somehow it is easier to do that. But that's beyond the scope. It's just it's important to know that we have this thing of alignment. So what happens usually is, okay, let's say X is box here, then it's 8 bytes, it's 64 bits, right? So it needs to be 8-byte aligned. So if this were just a struct, right now we're just thinking of this struct, right? It's not going to be 12 bytes, which is what you'd assume. This is 4 bytes, this is 8 bytes. It's going to be 16 bytes. And 4 of those bytes will be useless, but the reason is this means we can have an array and everything starts at an 8-byte aligned value. Like the first one will start and then the next one will start. But if we tried to pack them in there, then we couldn't use the optimized instructions to load the second or the third, or at least we couldn't use it for the second because it would be at a 4-byte aligned address. Some multiple of 8 plus 12 is no longer a multiple of 8, but some multiple of 8 plus 16 is. Does that all make sense? Yeah. Okay. So then the last thing is we've talked about, or I've reviewed like alignment and structs or whatever, but there's one extra bit of information we have to store with foo. If we have enough room for this, we also have enough room for this, right? assuming T is box. But we also need to record which variant we're in. So there's probably another byte. And I'm sure the Rust compiler is smart about where exactly that byte goes to try to minimize wasted space, right? And that byte will just have like the value 0 for none, or the value 1 for third variant, or the value 2 for some, or something like that, right? So, so when we load it in this match statement, it doesn't like it because we're not covering all of the match cases, right? Because I added one. If we load it in this match statement, then we can look at what it's actually doing is it's looking at that little byte and seeing which variation it is, right? But this might make you think, okay, what about option again? If we're using this, when we would use like let's say we're using option box every time that in C we would have used option, or we would have just used a pointer, right? Or many of those times. This seems like it's wasteful, right? Because we store the box here. That's 8 bytes. So far, so good. In C, a pointer also takes 8 bytes. But then we have to store another byte to figure out if it's none or some, right? But there's a trick with this. The compiler is aware that a box can never be all zeros, because all zeros is not a valid value for a pointer to something. Like nothing can be at address 0. Rust still has that rule. And a box can never be all zeros because a box can never be null, right? So if T is a box, that can never be null. So the Rust compiler does something called what is it? Niche? No. Well, she calls it the null pointer optimization, I think. Yeah, this is where she's talking about it here. This is in the first list, first layout thing. The null pointer optimization thing is actually just what Rust will do this for anything. Option is not special. Any enum that looks sort of like this, where this is like box or something else that can't be null, Rust will manage to pack this enum into exactly the same space that this took. Because all it does is it says, if this value, or if the whole thing is anything other than 0, then I know we're in case B, and I know we contain a non-null pointer, right? I know we have a box. But if it's 0, that's how I tell that we're in case A. So the Rust compiler is insanely smart and takes advantage of that particular optimization. And I think it has a more general solution where it'll try to find what are called niches, which is values that are unused in a type. Like a type has a size, but a type also has a set of possible values. And usually those sort of match, right? Like an integer is 64 bits wide and it could be any 64-bit value. But a pointer to something like a box or a reference, it's 64 bits wide still, but there's one value that's unused, 0. So Rust will take advantage of that and will shove other stuff in there if you put that type in an enum. This is called niche optimization, or niche optimization in Rust. Is it called niche optimization or niche value optimizations? Maybe, but niche just for like the small space that we're fitting into. I don't know. I think that's cool. That's basically all I know about option and enums. So yeah. Do you have any questions?
Cool.
Okay. Yeah, because without this, then option of box or whatever would be wasteful, Here, it's not. It's exactly the same size, 8 bytes, as it would be in C, you know, as a pointer would be in C. Okay, that was fun. Uh, I'm actually going to go ahead. I just don't feel like doing this again. I'm going to go ahead and start on third. Did you take 341?
Yeah. I mean, I had to with bachelor's
Right.
degree and stuff.
Oh, right. Oh, yeah, 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 yeah. You graduated and all that. Hell yeah. So you've seen F sharp or Haskell or something? Was it F sharp?
Unfortunately.
Okay. But it was, here's just like her way of writing how lists work in those sorts of languages. Um, we can have a list, it's singly linked, right? Then we can create a second list that is the tail of the first list. So that's everything except for the first thing. So it's just going to be BCD. And then we can try to have a third list where we push something new onto the second list. And that results in the value X points to B, points to C, points to D, right? And in memory, what that sort of looks like is we have a list one variable that points to A, which then has its as its next B, and then like we share this tail is the important thing, right? And you see how these are related and how so what she says, this is a persistent list. A persistent data structure, this is sort of a vocab thing, but a persistent data structure is one where operations on it preserve the previous version of the data structure. So none of these operations destroyed anything. We just had a different way of looking at it, and then we built something new out of that, right? But we didn't mutate anything. We didn't. If someone still held a reference to list one, nothing changed for them, right? Um, so that's nice. But the issue is we can't do this with box because with box, there's one. Okay, maybe you could somehow if you had like you can't do it fully freely with box because with box there's one thing that's going to free the memory for our items. There's just one bit of code, right? The destructor for box. As soon as the box is dropped, as soon as its destructor is called, a list goes away. So what we want is we want not just shared access to data, which is we already have references, shared references. Those are good for that. We want shared ownership of data, which means that it's fine for like as far as we're concerned, we don't have to care about the lifetime of other things, right? The iterator was tricky because it cared about the lifetime of the underlying list. We couldn't return the iterator from a function that owned the list because if we returned that iterator, it wouldn't work without the list, and the list would be destroyed when we returned, right? Um, but for shared ownership, what we want is we want the idea of we each like have the ability to keep this thing alive. Like this will not go anywhere no matter what. But we're both looking at the same thing. So the simplest way of doing this is reference counting, and that's what Rust uses. Other languages use garbage collection, which is kind of magic, but that's a topic for another time. Reference counting is better suited to Rust because the notion of Rust is that you only pay for what you use, and typically languages with garbage collectors, the garbage collector is just always on, and even if you don't need to do shared ownership, you need to be using the garbage collector, right? Java, everything is garbage collected. Python is the same way. Most languages with garbage collectors are. But whereas here with reference counting, we only use it for special types that do the reference counting. RC is our shared pointer, a pointer that allows us to share something, right? Like share this B or share this C. And RC stands for reference counted, right? But what does this? Well, where was I going with this? Reference counting works pretty simply. Let me draw a diagram. Uh, this is actually there's sort of a theme with this and enums. Let's say this is a node of T, right? So we have a node. If we had a box, what would that look like? That would just look like, okay, we have another thing that's like a box of a node of T, and you draw an arrow somehow, like this, right? And that's all we need for a box. Are you following so far?
Yeah.
Okay. So let's say I want this fancy thing, this RC that just keeps the node alive, but multiple people can have RCs that point to the same node. So I can have a situation like this, right? And these can be owned by different functions, or they can be part of different structs. So they could be dropped in any order. And what we need to do is when they all get dropped, then this also gets dropped. But until then, we don't drop this. Okay. So so it works by keeping a reference count, a count of the number of RCs that are live, a number of RCs that exist to this particular thing. Where do we put the reference count?
You mean physically in memory
Yeah,
or
physically
just
in memory.
logic? Oh,
Well,
shit.
physically in memory,
Okay.
like relative to these boxes. Like I'm gonna create a new box that's like the reference count.
It would
Where
have to be attached to a node,
yeah, it
right?
would have to be something
So
like here, right? Yeah. It can't be on one of these guys because the reference count needs to be something that we all agree on, right? So yeah, so actually instead we're like pointing here, but this gives us, I mean, we're pointing to the whole, these two are contiguous, right? I wish I could easily make it, um, I want to make it outlined. Whatever. These are contiguous, right? Um, but they're separate. Okay, so we have this reference count. And anytime like this goes, right now, what is the reference count? Like, what is the actual value for this diagram? 2, yes. So then if I get rid of this guy, it becomes 1, right? Okay. So the way this works is pretty simple. There's an important thing to note, which is that what people normally mean when they say garbage collection is they mean tracing garbage collection, which is yeah, this is a good summary. It will dig through all the memory that's sitting around at runtime and figure out what's garbage automatically. Um, and how it does this is that periodically it will look at all your memory. Um, and this means that the language has to be kind of safe, meaning like we have a language level concept of what is allowed to point to other things. Um, so like Python and Java are well suited to this because in Python, just every variable is a pointer, basically, right? Every variable is a reference to another object. Nothing is stored in line, at least not normally. Um, and the language knows about this. This is not something that I have to deal with. You know, I can't easily observe the value or change the value of a pointer. I can't be like increment the pointer by 1 to Python, you know. Same thing with Java. Java doesn't let you do that either. C lets you do it. So C is it's a lot harder to make C garbage collected. Um, that's kind of beside the point. I guess the actual point is just their overall algorithm is periodically they look at all your memory and they know that certain things are things that you might use again, right? They know that you might use anything on the stack. They know that you might use anything in globals. So they start from there and they follow all the pointers. And then they say, okay, those things need to stay alive. Everything else on the heap, I can free. That's how tracing garbage collectors work. The tracing refers to the step of following all those pointers, right? Reference counting doesn't do that. Reference counting works by just as you operate, incrementing and decrementing the references, the reference count, right? And then when this hits zero, this goes away. So two important things. One, it has significantly less throughput than a tracing collector for many workloads. Now, I can't like independently verify this. I haven't done any tests, but clearly she knows what she's talking about. And you can kind of understand why tracing garbage collector doesn't actually have to do anything uh, necessarily for like all the operations in your program. Tracing garbage collection just needs to run periodically. Whereas reference counting needs to like do these little increments and decrements and tests for if it's zero all the time as you're passing pointers around, right? Um, so that can actually cause it to be slower. That's what she means by less throughput than tracing garbage collection for certain kinds of things. Tracing garbage collection typically is sort of um, lazy about actually collecting memory. It waits actually freeing memory. Tracing garbage collection usually waits until we're almost out of memory to really do all of the steps, which makes sense. Memory you're not using is completely wasted, right? Um, but this is but it's not like it's free, right? Other programs might have wanted it. But this is why, Java and other garbage collected languages are sometimes have a reputation for being pretty memory hungry. They just what they do from the outside perspective, from the perspective of other programs or from the operating system, is they just reserve a big chunk of memory, and then that's like almost independent of what they're doing. I mean, obviously that there are settings, and maybe they don't reserve that much. But if you've ever seen the heap size setting for Java, or when you're running Minecraft or whatever, that is just like reserve this big chunk of memory. And probably the operating system doesn't actually reserve physical memory at that moment, but then Java, your program is running and it creates things and then it loses track of them. It no longer has pointers to them. But the garbage collector doesn't immediately clean up stuff. The garbage collector, if it was immediately cleaning up stuff, then it would be kind of slow and it would be interrupting your program a lot. So instead, it waits to run, and garbage just builds up in your memory. And the operating system, no one knows that it's garbage yet. But then eventually, you're almost at capacity of how much memory can be in the Java heap. And then it runs a collection and it realizes that like, oh, 90% of that I didn't need, and it frees it. Right. But in that in between time, that program was very rude to other programs because it pretended to need more memory than it did. At the same time, maybe that's way faster than reference counting because it didn't have to be doing anything when you were passing pointers around. It just deferred all the workload till later. And then later only happened when you were almost out of memory. Right. Um, so, there's no silver bullet. Rust can actually be slower if you do things like use RC all over the place. But it's still useful, and RC is still pretty simple, and I think it's a good thing to understand. Another thing is it completely falls over if you manage to build cycles. Okay, what is a cycle? Do you have also is this new to you or is this review? I'm just trying to gauge this.
Well, what you would say?
What?
I
More
do
more of a review? Okay.
more. Yeah, so I do
Okay.
remember this stuff from the F sharp.
Okay.
It it's coming back to me.
Right. Another important thing is Python. Some people will talk about Python being reference counted. It is, but it also has a backup garbage collector. So most of the time it's reference counted, but then sometimes it'll run a garbage collection cycle or a garbage collection like tracing thing. A cycle, though, I just want to quickly do this. Um, what if our node had an RC inside of it? And what if that RC, oh God, I need a curvy arrow. I don't think that's an arrow. This app kind of sucks. But whatever. What if that RC was pointing to itself? Okay, the reference count is still 2, right? What if I drop this? What happens to the reference count?
Drops to one, and then the object stays up until the
Yeah,
end of the runtime.
yeah. And this looks very silly. Like, who would write memory like that? Who would make some program like this? But someone might easily make a program like, um, what am I doing? Ugh, I need the curvy. What the hell? How do I? This is some bullshit. Just, I just want an arrow that's curved. Like what? It's not too hard. Not too much to ask, Apple. I guess it is too much to ask. Whatever. You probably see where this is going. We have that, and then we have an arrow that I will draw as a line just to be silly here. And actually, let me think. This only has a reference count of 1. And 1 second. We actually have 2 RCs. So one of them's like that. This one doesn't point to anything. This one points back. This one also has another one. And this is the one. This guy points here. Okay. What is this data structure? Probably.
I'm not sure.
A doubly linked list.
Huh.
We have a node. These are our nodes. They're behind RCs because we need 2 pointers to them,
Hmm?
or at least sometimes, right? So I'm jumping ahead, but we'll see this. We need 2 pointers to them. We need them to be pointed to from the thing before them, like this, and we need them to point to the thing behind them. So this guy ends up pointed to twice, by the head and by the thing next to it, right? So this is a doubly linked list with 2 things in it. There's a problem, which is if I lose the head, then reference count of 1, and the whole thing stays alive, right? So this is actually why Python has a garbage collector. It's to solve problems like this. Yeah. Okay. That was mostly review, but I will get on to just a little bit. Yeah, I'll say one last thing. Okay. So where does she talk about it? Let's first start looking at this code. This was our code before. Um, what if we just change the box to RC, which we only have to do here? It doesn't work because we can't find the type RC, because RC is not by default imported into everything, unlike option and box. But you can easily import it with this use thing. Um, so I'll just copy this. Sure, whatever. Uh, okay, yeah, I have that problem. Import std RC. Okay, cool. Right now we have exactly the same situation as her. That's the layout. When we're making a new list, that's very simple. Head is still an option, so the new list has nothing in it, so that's none. But okay, so let's not really call them push and pop. Let's call them prepend and tail because they don't modify the old version. So prepend is like make me a new list with this new thing on the front. Tail is take the front thing off. Like give me the tail of the previous list, everything except for the first part. Does that make enough sense? Yeah. So yeah, let me just try writing prepend. So this will take, what will this take? This will take a reference to self. Everything will be taking an immutable reference to self, if I understand correctly. Because we don't need to take ownership. There's no reason for this to be the last method you call on the list. And we don't need to modify it, right? So this doesn't really do anything because our type is entirely immutable anyway. Also, this is important. So RC works like box, except you can't modify the thing inside it. So RC already allows you to do, already enforces that. And the reason is by default, Rust has this rule of mutable XOR shared. Exclude like either it's mutable or it's shared, not both. XOR for exclusive or. Um, And just like shared references, you can't modify through them. RC, you can't modify through them. There are ways to get around this, but that's the default. And the reason is exactly the same reason why it's impossible to get around it, or why it's hard, why it's the default with shared references that you can't modify things through them. It's because it's confusing to have multiple things modifying the same thing, right? So here, what should we return? We should return a new list. Or I guess, what the fuck? Like this. We should return this. Because prepending will create a new list. So what do we need to do? We need to say, I need a list. I'm going to fill the struct fields. Oh, it's just head. I should have just typed that. So we need to make a new RC. You do that with RC : new, like box. And oh right, prepend needs to take another thing. It needs to take what we're prepending. Right. So we call prepend with like another element, like another integer or something, and then we say, let's make a new RC, and it needs to be an RC of a node. So we need to pass it a node with an element of elem, and then the node's next needs to be our current head, right? We're returning a new list that has the same, like that continues to have all of the elements in our current list. So we need to say our current head somehow, right? Okay, so what if I just try to pass self.head, right? I get a bug, but it's actually okay. Head needs to actually be some of this because head is an option. Does that make sense? So in order to create an instance of an enum, we have to specify which variant. And here, head is an option because head is a link, which is the same as an option. So we need to say head is some RC with this new node in it. And then its next is our head, right? So this all looks right, except now we have an issue here. Sorry, am I going too fast or did you kind of follow that?
No.
Okay, yeah. Now we have a problem. This is our old friend cannot move out of self.head, which is behind a shared reference. Okay, what the hell? I just spent some time saying RC let you share things, and now it's trying to move, even though I'm just trying to copy this self.head, right? Here's the trick of it, and I'm glad I explained copy and clone because that makes it easier today. RC is something that you can share. You can duplicate an RC and end up with two RCs to the same thing, right? Like these guys. Um, but when you do that, you can't just do that by uh, copying the bits. Like with an integer, you can just copy the bits, right? With RC, I have to do an extra thing. What's the extra thing I have to do with the RC when I copy it, when I duplicate it?
Duplicate the reference counter as well.
I don't have to
What?
duplicate the reference counter, but I do
Okay.
have to do something with it. There's only one reference counter, even though we have multiple RCs. The reference counter is on the node, like you said.
Mhm.
I'll bring,
So
yeah.
yeah, so we need to have uh, a connection or a pointer perhaps to this RC, right? To the reference counter.
Right. So the RC actually is a pointer to the beginning of something that it has the reference count and then it has the data. This is all one allocation. So we only need one
Mhm.
pointer in the RC. That's an important thing to know. But there's something we have to do. Let me make it simpler. Um, what the hell? I search box, but this doesn't come up. Okay. Uh,
It's not a box; it's a square.
uh, and then I have another thing that's a node. Okay. So far, so good, right? We're
Mhm.
pointing at the whole thing. Okay. I want to give you a new RC, which means that you know that this thing will stay around as long as you have this RC, right? So I copy it and I make this point to the same thing. There's something else I need to do right now. Here's the problem. One of us loses our RC. Then the destructor runs and the reference count falls to 0 because the
Um,
destructor decrements it. You see what we were missing now? What did we have to
yeah,
do when we copied it?
we, we have to increase the counter itself.
Yes. Okay. So because of that, Rust has like really strict rules for what it means to copy something, right? Rust's rules for
Yeah.
copying are it has to just be the bit copy. So the only reason why RC can't implement copy is because it has to do that increment every time. So RC implements clone. But it's important to note that when RC implements clone, so what we can do is actually self.head.clone, but I don't recommend this. This works because we created a new RC here. But what's confusing about this is that what if our thing that's head also implements, like what if our thing inside the RC, here the thing inside the RC is a node. What if it also implemented clone? This sort of looks like we're calling clone on that because RC is a pointer. So, by default, I could do something like .elem. I mean, that doesn't work because it's not the right type, but that works as far as it goes. It just fails. No, it's okay. I could do unwrap, right? Because this is head is actually an RC to an option, right? Um, it's a no. What is it? Head is an option of an RC. No, so I need to unwrap it before I can get to the RC. But now I could go to the elem, and my problem is not that I can't just go straight to the elem. It's that um, I'm finding it's the wrong type. Elem is of type T, right? The point is this dereferenced RC all on its own, right? So this actually isn't really a problem here. There's no confusion here because head isn't. No. Head is an option of an RC. Okay, yeah. So if it weren't an option of an RC, if it were just an RC, let's imagine head is just an RC, right? So ignore what the compiler says for right now. Imagine head is just an RC. This is kind of ambiguous because I could be calling clone on head, but I might I could be calling clone on the RC, which just duplicates the pointer and increments the reference count. Or I could look at this and think just semantically, head is really a node. And maybe node implements clone. Maybe I'm calling clone on the node and I'm creating a new node, which would be a different thing. So in Rust, this always means that we're calling clone on the RC because that's immediately what's here. Head is an RC. It doesn't dereference to find a method, right? Because it can find the method right on RC. But in order to avoid this potential confusion, what we do is we use a different syntax for calling it, which you can actually use with any method. We do RC colon colon clone. What's going on here? What? Wait, what? How do you do this? Self.head.clone. So she just does this. Right. Okay, so here's the problem. We can't actually do RC colon colon clone here because this isn't an RC, it's an option. What we can do, we basically have to do dot clone here, but it's important to note that when we do self.head.clone here, we are only cloning the pointer. We are not cloning the underlying node. So when I was saying earlier that like copy is just a shallow copy, but then clone could be a deep copy, that could is important because with RC, clone is not a deep copy. Clone is still a shallow copy. It just copies the pointer and increments the reference counter. We'll see later what I was talking about with RC colon colon clone, but I think that's a good place to stop right now. Do you have any questions?
Oh,
Okay.
I think so.
Yeah. So yeah, this should work. And once we have tail, we could actually test it. But yeah, what this does is it duplicates just the RC, but we're pointing to the same node. So this is already a kind of useful type, right? This is already some good code.